Yes, I suppose.
All right, we're live, but we're still waiting for Benedict, who will do the introduction. So, folks, please pay no attention to the clock. And I see that Benedict is here. So,
Hello.
Benedict, take it.
On time.
Okay, yeah. Thank you for your patience. Thanks everyone for their patience with the technical obstacles that we are facing. But I think it's gotten much better now. And I'm very happy to announce the next speaker, Dominik Kirst, who will give a talk on the generalized continuum hypothesis and the relationship to the axiom of choice in HoTT. Thank you, Dominik.
All right, thank you for the introduction. And this is joint work with Felix Rech. I will step through the presentation. Please let me know if something weird happens. Hopefully everything will be good. So I want to start with reformulating the title a bit and drop the HoTT and use ZF here and see what the theorem actually says in standard set theory. So it says that the generalized continuum hypothesis, so the fact that there are no cardinalities between an infinite set and its power set, always implies the axiom of choice in the form that every set has a choice function, or in the equivalent form that every set can be well ordered, using called the well-ordering theorem. And the history of this result is that it has been announced already in 1926, so in very early stages of axiomatized set theory by Lindenbaum and Tarski. But they didn't have a proof, and the first to publish a proof was actually Sierpinski in 1947. And it seems like Gödel had the proof also before in one of his unpublished notebooks from the early 30s, but Sierpinski's proof was the first one. And afterwards, there was a bit more work in trying to localize the proof a bit more, so minimizing the instances of GCH you need to prove AC. And Specker was the one who gave the strictest result, shrinking it to just 2 instances. Okay, then there's the more recent picture, mechanization of this theorem using proof assistance. And the first here was Carnero, who proved the result for axiomatized set theory in MetaMath. And then we had a paper in this year's CPP with the same title, but with Coq instead of HoTT. And there we had 2 variants of this result. One variant in higher order ZF, so an axiomatization of ZF using higher order logic. And then also a variant using Coq's type theory itself to represent set theory. And the basis for this can be maybe summarized in this picture. So it's clear that on a very abstract level, foundations like type theory and set theory are concerned with the same things. You have collections, you have operations on these collections. And this means that many results from classical set theory will also be results interpreted in a type theory. And the interpretation is as follows. So the lucky thing in Coq's type theory is that by default, you have an impredicative universe of propositions, which gives you a notion of propositional existence. And then you can interpret set membership as the typing judgment for any types X. You have power sets because of this impredicative universe, because you can represent power sets as the unary predicates on the type. You have numbers, for instance, as represented as an inductive type. And then more derived notions like cardinality and orderings can also be represented. So cardinality comparisons based on the existence of Z-theoretic functions that compare the cardinality can be represented using type-theoretic functions and anonymous existence. And for orderings, so relations with particular structure, you also can use type-theoretic relations. So this means you have all the ingredients available to express a theorem like GCH implies AC. But then the problem is that in Coq's type theory, this is not exactly well behaved. So it differs a bit from set theory, mostly because Coq's type theory is much more intentional. And so what we had to do in the proof before is we had to do a lot of assumptions. So for instance, we assumed functional extensionality and propositional extensionality, so that the function space and the predicate space behave as you would expect it in set theory. And also in set theory, there is no difference between a function and a total functional relation. And to remedy this, we needed to assume the axiom of unique choice as well. And this left us kind of unsatisfied with our development. And so we were thinking that this might be a good case study to use HoTT instead, because here the situation is way more well-behaved. So at least if we assume propositional resizing, so we can represent propositions in the lowest universe, then we also have the notion of membership. This time we can look at the H sets in particular. We have a power set available then, and we can use the same natural numbers and truncated sigmas for cardinality and orderings. So this is basically the same, just in a slightly different type theory. And now the advantage is that uniformly, by just assuming univalence, you get enough extensionality. So this representation behaves like set theory. And also unique choice is provable by the elimination principle of truncation. So the result here is now really, you don't need more of these ad hoc axioms. And then we, what this talk will basically be is an experience report how transporting a mechanization to this different setting might look like. All right, so first we have a look at the formulation of GCH in HoTT. The basis for this is, as I already mentioned, cardinality comparisons. So we need a notion of when a type X has smaller cardinality than a type Y. And the definition we choose is the mere existence of an injective function from X to Y. And with this, if we have a look at the informal statement again, there are no cardinalities between an infinite set and its power set. We can now formulate this as quantifying over all sets, in particular looking at the infinite sets, and then the situations when one set is squeezed in between a set X and X's power set. And then positively, we can say that the GCH then asserts that one of these inclusions here can be inverted. So either Y is already below X or Y is above X. All right, so this is the formal statement. Then an immediate observation is that this is in fact a proposition, because the conclusion here is exclusive, because otherwise we would get an injection of the power set of X into X, which is ruled out by Cantor's theorem, talking about injections. Then we have decided to formulate it this way because we needed it in the proof. So without having the axiom of choice available, you really need the existence of these injections here. You can't just do something like there is no set strictly lying between in those. So here you have to be a bit careful. And then on the first glance, this might look a bit weak, because normally one could also say then one of the cardinalities here must be equal. And here we observed, and then also found published, that already a weak formulation of the continuum hypothesis implies excluded middle. So you get, as soon as you assume the continuum hypothesis, you get classical reasoning available, and then the structure is a bit more easy. So we will see this in a second. So first, let's have a look at the statement. This is just the continuum hypothesis, so the instance of GCH for the natural numbers. And now the claim is, if this holds, then from it we can derive excluded middle. And the proof is basically just using the right type for X, the set in between, and we use the type of all singleton predicates on the natural numbers. So either P is a singleton, or we assume a decision for P or not P. And then we can show that this type X satisfies the condition here. So it's squeezed in between the natural numbers and the power set. And that's obvious because it's a subset of the power sets, and in particular contains all the singletons. Then the next observation is that we can refute an injection of X into the natural numbers, because this would give us a negative claim, so we can do a classical case distinction. So we have a proof of P or not P, but in the second we have a proof of P or not P, this whole set blows up and becomes the full power set. So we can refute it again using Cantor. This means that only the right-hand side here can be true, so an injection of the power set of the natural numbers into X. And here then again, by a variant of Cantor's theorem, we can construct a particular predicate such that its image under the injection is not a singleton. And if we were able to construct an element of X which is not a singleton, immediately by this we get a proof of P or not P. And so we have proven the excluded middle from GCH, and this also means as a corollary, because then the Cantor-Bernstein theorem is available, that we could have equivalently formulated GCH even strongly with cardinality equality here, meaning by univalence actual equality. So that's a pretty strong formulation of GCH that would actually be wrong in normal set theory. Okay, so we have now discussed a bit about GCH. We have seen the proof to the excluded middle, and I want to now first give you a little tour through the full proof, so how to get from GCH to AC. And then I want to give you a few remarks on the experience of transporting the mechanization in Coq to the mechanization in HoTT. Okay, so first the outline of the proof is that instead of showing the axiom of choice, we show the equivalent well-ordering theorem, which means we have to well-order every set, and to well-order a set, it suffices to embed it into an ordinal. And to have enough ordinals, we need to do one central construction, namely the construction of the Hartogs number of a set, which is a large ordinal in the sense that it cannot be embedded anymore into X. And it's large, but still not uncontrollably large, so it's possible to give a bound on it in terms of an iterated power set. And if we have this construction in place, then we need to develop a bit of cardinal arithmetic, and here the problem is in the absence of the axiom of choice, where cardinal arithmetic behaves a bit different than you would expect. And then finally, we can use GCH to iteratively to squeeze in the bound here, such that we finally obtain that instead of having an injection of the Hartogs number into X, we always get an injection of X into the Hartogs number. And then we can transport back the ordering and would obtain the well order on X. So that's the route to the result. And we can now have a quick glance just at the constructions involved. So the first part is ordinal theory. And here's nothing really new. So we just follow closely the HoTT book in their constructive definition of ordinals as sets equipped with well-founded extensional transitive mere relations. And then we need a bunch of the standard results about ordinals. So for instance, as an instance of the structure identity principle, that isomorphic ordinals are equal, and several other constructive results. But we also need one classical result, namely that if you assume excluded middle, or in our context, assuming GCH, ordinals behave classically. So they are trichotomous, and for every non-empty subset, they actually provide a least element. And we also do some more. So we also construct successor and limit ordinals, but that's not relevant for the main result. Okay, so then the central construction. We want, given the set X, to construct its Hartogs number. We can't use the axiom of choice on this, so we deviate a bit from one way how you can do this construction, but in fact, we are pretty close to a normal set theoretic outline of this proof, which would normally say that we define the Hartogs number as the ordinal containing all the ordinals that admit an injection into the type X, and then we use the normal ordering on it. And then in set theory, you would have to show that this is in fact a set, so it's small, because if you just write it down like this as a class, and here in type theory, we have something similar, because here we increase the universe level because we quantify over all ordinals. And what we need is a construction staying on the same universe level such that we can repeatedly apply it. And this works by the means of the following theorem, which, asserting classical logic, gives us a resizing of this preliminary definition of the Hartogs number to the actual definition and along an injection into the threefold power set. And then we can conclude that this is on the same universe level because the power set doesn't increase the universe level. And we have the specification available. So we have the bound upwards against the threefold power set, and we have that the ordinal is larger than the set. And the proof is, I could just give the main idea, that's to construct this injection of an element of the Hartogs number in this preliminary definition, which is an ordinal which embeds into X. And along this embedding, you can well order a part of X. And we just map it to exactly the class of all partial well orders that are isomorphic to the ordinal you start with. And this needs a bit of classical logic. And then you're directly done because you can obtain the Hartogs number as the range of this injection. You immediately get the bound because it's a subtype of the threefold power set. And conversely, if you would have an injection of the Hartogs number of A into A, then just by the definition, you would see that you have derived the Hartogs number to be an initial segment of itself, which is, of course, refuted by the well-foundedness of ordinals. Okay, so this is the construction, and here we can remarkably close follow a set theoretic outline, which is really nice and hot. Okay, then the next ingredient, cardinal arithmetic, is needed to derive enough equivalences on types, so the main construction works. And for instance, facts that we are interested in are to do with largeness of types. So for instance, in normal set theory with the axiom of choice, you can always show that an infinite set, if you double it in size, then there's no increase in size. And this works using the axiom of choice, and I think it's even equivalent to it. And without the axiom of choice, you get something slightly weaker. So then, and also using classical logic, you get that every infinite set, so a set with an embedding of the natural numbers, satisfies that if you double its power set, then this is not larger than the power set itself. And as an intermediate step, we also show, for instance, that you can add a point to the set without increasing it. And the proofs are mostly by constructing equivalences and then doing some equational reasoning. For instance, that's the derivation of the equivalence between the power set of X and 2 times the power set of X. And here, for instance, you see where classical logic is needed. We need to rewrite the power set of the singleton type with the Booleans, and that's, of course, classical. Okay. We can then call a set large enough if it satisfies the property that we are actually interested in. So you double it and it doesn't increase. And then, for instance, large enough sets satisfy the following theorem. If you add to a large enough set a set Y, and then you can show that the power set is below the sum, then the power set must already be below Y itself. So X cannot really contribute much to the size in comparison to the huge size of the power set. And I can't talk about the proof much in detail, but again, the main idea is, again, the Cantor-like argument. So the gap between X and the power set of X is really, really big. And so from an injection here, you can just refine it into an injection into Y. Okay, so now we have the ingredients in place and we can look at the main construction. So we want to show that X embeds into its Hartogs number. And we do this in a more general way. So we abstract away and say that for every function on sets that preserves the universe level, which has similar properties as the Hartogs number. So it's bounded by some iteration, by some finite iteration of the power set. And it's you never have f of x below of x. Then we can show that for every large enough set, in the sense as before, we can actually show that x embeds into f of x. So GCH normalizes this function f. And the proof is actually not that hard. You do it by induction on k. In the base case, the assumptions are contradictory. And then in the inductive step, you just produce a situation where you can assume where you can use the continuum hypothesis. So you squeeze the sum here where you add f of x in between the k-fold and the k+1-fold power set. And then you can, there are two cases what GCH does to the situation. Either the first comparison can be reverted. And in this case, you can, because then the sum is below the k-fold power set, already f of x is below the k-fold power set, which then lets you proceed with induction. And in the second case, we have the situation from the lemma before. So we have a sum here, and one half of the sum is taken to the power on the left side. So we can just leave it out in the sum here. And by this, we can derive an injection of x into f of x. So this is almost completely done by cardinality arguments. And then in total, we are done. And the quick corollary is that if we instantiate with the Hartogs number, then this is enough to derive AC from GCH. Okay, so much of the proof outline. Now in the remaining time, I want to quickly give you some observations that we made during this project. So first, about the mechanization itself, it's based on the HoTT library and has been merged into the library. And we contribute these developments on cardinals, ordinals, the Hartogs number that were necessary to get our results. And also, as a fun fact, 5 versions of Cantor's theorem. If you're interested, I have a backup slide where these versions are listed. In total, it's rather of a compact size, and more than half of it is concerned with ordinals and the construction of the Hartogs number. The rest of the argument isn't that heavyweight. In fact, some code could be reused from the previous development, and in particular, using the HoTT library for someone who is not trained in HoTT but used to working in Coq is quite easy, because tactics, notations, that's all pretty similar. And also there's the type class support deriving HProp instances automatically, so you don't have to worry too much about this. And the only difficulties we experienced had to do with resizing and power sets. So basically, one problem is that resizing by hand can be tedious, because you always have to transport along these representation equivalences. And also performance-wise, this can get pretty slow sometimes. So in fact, we defined the power set slightly different. We didn't restrict to the lowest universe and only resized where needed. And this was in particular hard for the construction of the Hartogs number itself, because here we afterwards had to make sure that we can resize it again into the correct universe, and it wouldn't work if we tried to inline it. Yeah, that was a bit more intricate than we thought. All right, and then in comparison, which is probably the most interesting thing, to the previous development, we can say the following. So first, all the proofs concerned with cardinal arithmetic and the main result can be done completely as we have done them before. And here even we benefited from using the HoTT library because some of the equivalences were already there, so we didn't have to do them again. Then the proof of the Hartogs numbers is completely different from what we did in the previous mechanization, because there, in Cox type theory, you don't have an actual well-behaved notion of ordinals, so we couldn't do it in this well-organized set-theoretic way that we could show here. Then, of course, the big selling point is that we didn't have to do setoid rewriting because we have univalence, and that was really helpful in terms of this project. For instance, we needed to prove lemmas before that if two types have the same size, then so do their power sets. And of course, that's just rewriting with equalities in HoTT. So overall, we could reduce the code by a considerable amount. And as I said, much of the code looks well more principled than what we had before. Also, on the more theoretical side, it's of course more satisfying to be in a well-behaved type theory where you don't need ad hoc assumptions to make a result provable. And the only caveat is really that, of course, Coq users are used to having a static universe of propositions and static impredicativity. So it was slightly unexpected and sometimes really intricate to work with dynamic propositions and make sure that you get all the universe constraints right, because sometimes they are hidden so implicitly that it's hard to figure this out. Okay, and this leaves me to the questions that I want to leave you with. And because the first question is whether it couldn't be done that you use in the HoTT library a static universe of H-props, where you can avoid resizing by hand. So you have resizing more inbuilt. And I noticed that Hugo Abelin is working on this, and I'm really much looking forward to seeing how this goes, because this would have helped us a lot. Then it would be interesting whether you get somewhere interesting with just using light HoTT. So instead of full univalence, just weak univalence, which is still compatible with UIP in the prop universe that Coq users are used to. And then more theoretical questions. It would be interesting to see whether GCH can be meaningfully stated for higher types. And what would be really exciting to see is whether you can define GCH more constructively, in the sense that it doesn't immediately imply excluded middle, and whether from this you still get some constructive version of the well-ordering theorem. Okay, and I want to leave you with these questions, so thanks for your attention, and I'm looking forward to the discussion.
Thanks a lot, Dominik, for this great talk. Let's give a round of applause. Are there any questions for Dominik? Andre has raised his hand. Andre, are you joining us?
Yes.
Yes.
Perfect. Can I ask a question?
Yes, please. Thank you.
Hi. So you mentioned that univalence was useful for some rewriting, but it didn't seem essential, right? At least the example you showed, you could have shown by hand that if X and Y are equivalent, then you get the desired equalities. So are there any essential uses of univalence, or could you essentially do the same thing in some sort of what Martinez-Cardo calls Spartan type theory? So you just have propositional truncation and maybe something else, but no univalence.
I think, yes, the proof can be done without univalence, because we have done it in Coq just using extensionalities. But the thing where we really benefited from it was ordinal theory. And here we would at least need an axiom that then gives us the fact that isomorphic ordinals are equal. Because without a nice representation of ordinals, the construction of the Hartogs number is really ad hoc, because then you can just talk about the representations of well orders within a type, and you don't have a nicely uniform treatment available. So here, I would say that, and for this fact, you also need full univalence, not only weak univalence. So here, it really makes a difference. And that was really the part where on the theoretical side, the proof could be improved the most.
Thanks. I have another question, but I should go to the end of the line.
Okay, then I will ask a question that Dan Christensen asked in the chat. What is weak univalence?
Okay. Weak univalence is just a statement that from an equivalence you get an equality without the converse. So it doesn't necessarily give you distinct equalities for distinct equivalences. And that's something that, at least for me, being used to working with Coq a lot before having a look at HoTT as well, would be the more lightweight assumption. And it goes a long way. So basically, the second half, everything which was not about ordinal theory that I showed you in the talk, would just work with this weak assumption. And so this is, I would say, an assumption that is, because it's less in conflict with some other axioms you might want to add, like UIP, an assumption that would be interesting to see how far it gets you. But
okay, I'll invite everyone to join the discussion room to continue.